So for this first exercise, we first have to build the executable. So this is done by make fp as requested, and we launch it, and we see that it's popping out 2, and then this expression that means that there was a problem, and it's already saying us that there is a floating point exception. So if we launch GDB, it's loading the program like this. So we launch GDB with the program name, and we say we want to run the program. We would have some arguments. We would put argument 1, argument 2, but for that case there are no arguments. So we run it, and it runs. We see the 2 that was popped out before, but then it stopped. GDB stopped because it's catching this exception, arithmetic expression, and it's giving us the file where it happens and the line in this file. So it's line 8 in file fp.cc, and we can see this expression. So you can see I have the file open here in my Emacs already, and you can see that in line 8, which is this one, we're here. Okay, so as it was invited, we can do a list, and list is providing us the context of this call. And in this call, the first reflex that you should have is, okay, we have an expression which is very simple, and we have a and b that are indeed variables. So what is the content of these variables? So how can you know that? By print. You can print a, which is 3, and print b, which is 0. So we are dividing 3 by the number 0. How is that a problem? Well, there's no way we can divide by 0. So the program is refusing. So actually the processor is, and the program is saying, well, we cannot do that, so I won't do it. I launch an exception which is catched by the system, so the program stops. Now we want to know in the structure of the program how that happens. So you can use the backtrace command, which gives us a stack of calls. So we know that we are inside of div_int function, which is, and we are exactly, it's a div_int function, and we're in that file, that line. And this function was called actually by main in the same file fp.cc at line 20. So let's check. Line 20 is this one. So the first call of div_int is not the one that is a culprit, only the second one. And we can see that indeed y2 is equal to 0 and set to 0. We could have known that. So what we can do in what we call the stack calls, we can go up and down. So I can go in the context of the main function by saying up, and now I'm said that I'm at line 20 here. So I know where I am, and I can print y2, which is the second argument, and realize that it's 0. So the way to fix that problem is very simple. We cannot divide by 0, so for example we can say 1, which is more something that would be needed. So I quit, and I make fp. Okay, I relaunch GDB, I run, all fine. I launch the program, no problem. So I have solved the first exercise by only using GDB. Next, for the next sub question, I will use GDB inside of Emacs to show it works and how convenient it is. So for the second exercise, what we have to do is to study this program. So the program is named alloc.cc, and I'm going this time to show a bit how to use valgrind and GDB and Emacs a bit more, so that you can see how convenient it is. So for example, I just use the mouse. So if you go to tools, so I'm on the program, and if you want to compile, you can use the compile tool here, and it proposes some command on the bottom. So if you hit make alloc, so it was already selected because I tapped it once, and enter. So it does the compilation here. So I have compiled everything for that program. So now I know that it's buggy, so I will directly debug it. So I can click on debugger, and I want to debug the alloc. So what you have is a new GDB, and if I go to this window and I put the buffer of the sources, I will know where I am. So for example, I did not show that last time, but I can show you how to put a breakpoint. So I put a break, and I want to do it on the main function. So you see I have a red dot here that is showing where the program is supposed to stop if you reach that point. Now I run. Okay, and I have a small arrow here that shows that the program is actually stopped here. I can do a backtrace, and it tells me I'm in alloc.cc right now, and the line 9. And it's the only function because I'm in the main function. So now I don't know exactly where is the problem, so I just want to continue until some problem. It would be the equivalent of not having a breakpoint. So I continue. Boom! I have some messages a bit obscure printed to the screen, and I don't know where I am exactly. So I hit backtrace again. Ooh, this is a long list. I have a long line, so I want to go up and up to the moment I'm not anymore in a function of the system, but in one of my functions. Still not in my functions. Yep, I continue up. Oh, I'm in the main, and I'm at the very last error. So this is the kind of error that you have when you have memory corruption. It means that something happened before, and it goes visible to the program only at the very end, maybe when some cleaning of memory is done on everything. So, but it's most likely a memory corruption. And how we do under these tricks usually is, well, we use valgrind, because valgrind is going to give us a lot of information. So how do you use that? You just press valgrind and the name of the program, which is alloc, and well, /alloc, and you launch it. We have an invalid write of size 4, which is an indication of the type, and we know where exactly this thing is done. So it's the alloc.cc file at line 14. And what is the line 14? This is this line. I realize here that some mistake have been done. We are looping from I is equal to 1 to I is equal to NB element. But it's probably someone that used to work in math or in MATLAB that forgot about the C convention. It should be like this, because indexes of vectors start at 0. So if I save this file, poof, and I rerun again, so I recompile first. So tools, compile, enter, and I switch to the debugger, which is still living, and I rerun. And I am at my breakpoint here. And so the program runs, and we solve the problem.